Wow, thanks for coming, everybody. So I guess I'll start this by explaining, or I guess telling you all a little bit about myself. She gave my long-winded title. I work here at Harvard in the physics department and the Institute for Theory and Computation, but I'm fundamentally am an observer. That is, I deal with data. I go to telescopes. I'm not a theorist. So this is all, gathering data is a very important process for me, and gathering the best data that I can is kind of the great challenge of my job. That said, I'll tell you a little about what I do. Briefly said, I'm an observational cosmologist. So the goal of cosmology is to understand the way in which the universe evolved over time. And so we do that by studying the universe at different distances. We look farther and farther and farther away. We sort of catalog what we see and measure its properties. And because light travels at a finite speed, the farther away that you're looking, the farther back in time you're effectively seeing. That is, the light took longer to get here from sources farther away. So the stuff we see is actually coming to us from way back in time. So when you look in slices farther and farther away in the universe, you're actually seeing farther and farther back in time. So what you can do is measure the properties of the universe as a function of time and actually measure how it evolved, and not in the biological sense, but how it sort of ended up in its current state. And the reasons we do that I won't really go into, but they basically probe fundamental physics in ways that are interesting, but probably not what you guys are here to listen about. As I said, looking farther and farther away is important, and I'm motivated by gathering the best data that I can. So in order to do that, we want to use the best telescopes that we can. And we have a lot of great telescopes that have been constructed over the decades. There's some really nice facilities both in space and on the ground, in sites like, you ask about dark sites. Chilean Andes is a really dark site. It's like science dark. Mauna Kea in Hawaii, also very dark. Those are two of the places I have been in the past 2 weeks. Frequent flyer miles is also something I know a lot about. I could take questions on frequent flyer programs. It's not a problem. So I mentioned, we have a lot of great facilities all over the world, but we really want to push the bounds of what we can do with what we've built. And one way to do that is take advantage of telescopes that nature provides. And so that's sort of the inspiration of my talk, nature's most powerful telescopes. These are effectively telescopes in space that nature constructed for us. They're not quite as easy to use as the ones we build, but we use them nonetheless. It just takes a little more work to understand them. So the mechanism that we're sort of using here is, taking advantage of here, is gravitational lensing. So I'll go over what that is at the start of things. I'll show you some examples of what it looks like when you find them. And most of my PhD thesis work was finding a very, very large sample of these things. So I know an awful lot about this. How do I find lens galaxies? Right. So then we'll go into the process of actually understanding what a gravitational telescope is, how we use it, and what we need to know about it in order to kind of leverage it into a useful telescope. And then I'll go over some results at the very end. And this is actually a really, really well-timed talk because lensing is, I'll tell you a little bit about basically a new initiative that's going to use lensing to push the bounds of what we can see in the next few years with Hubble. It's kind of an exciting result. So I'm using the word lensing a lot, and I'm going to continue to say the word lensing an awful lot. You might get sick of it. And lensing here means pretty much exactly what it means in everyday life. It's just the redirecting the path that light travels along, except with gravitational lensing, you're doing it with gravity. In everyday life, you see it happen all the time. If you ever look in sort of like a swimming pool, things look bigger than they would normally be. The pools look shallower than they should be because than they really are because things are being magnified. If you look at a fish tank from one side, you see multiple images of the same fish kind of coming at you from different directions. All of that is just simple lensing phenomenon, and the way that it works is in this case, it's the actual interface from water to air. But something causes the light that's traveling to bend its path and change direction. And if that happens in such a way that sort of two light rays from the same fish, end up at your face, coming from two different directions, you think you see two fishes. Fish is plural. Let's not go there. When in fact, there is only one fish. There are also sort of distortion effects that I should sort of describe. The Matisse painting is kind of a joke because it's not really obviously a photo, but you can see pretty clear distortion going on here when where you're looking at a straw image through a glass. The straw in real life we know is straight, but here it's kind of obviously bent and cuts off in some places. And these are all just distortion effects that happen just because the light is having its path bent on its way to your eye. And so that's lensing. This is also a real life example of lensing. I spent 6 years in Chicago. If you've been to Chicago, you've probably seen the bean. except they hate it when you call it the bean, because its name is the Cloud Gate. That's the name of the sculpture. But everyone calls it the bean. It's an amazing sculpture. This is the view from, I think, just if you walk up underneath it, you can actually get under there. It's also just in some ways a giant, well, it's not quite a lens, it's a mirror effectively, but it's the same optical sort of principle. It's a giant reflector, but it's one that does not have a nice smooth surface. It has more of like a funhouse mirror surface. And a funhouse mirror is a really good example, or a really good point of comparison for a lot of the stuff that we're going to be looking at in terms of what we see in space. And that's when you build lenses, on the ground for, like, say, a microscope or for a telescope or for your eyes, you want to make those really smooth and really nice and really well behaved. You don't want your eyeglasses to distort things into crazy shapes. The lenses that we see in space have more of the properties of this kind of thing here, where they weren't constructed exactly for our use. They're kind of clumpy, blotchy, and the images they produce are really wildly distorted. And this actually is a really great visual image to get you prepared. So I'm going to show this one equation. I apologize if that's not what you came here for. I'll show it several times throughout the talk, and it's super easy. As I said, I'm an observer, so really this is not what I would prefer to spend all my time dealing with. Equation is, well, let's go through this here. The lens equation is here. It's shown twice. Same equation. Don't worry about it. Focus on one or the other. It doesn't matter which. It really only has three components. See? Super simple. There's beta here, which just represents the original position of an object on the sky. There is theta, which represents the apparent position of the object on the sky. And then there's all this other junk, which we don't really need to understand too well right now, and that represents the deflection of a light ray coming from the source that's being described by beta and theta. So in this case, we have a guy who probably looks a little like me, staring into space. There's something out here, let's call that a galaxy, and something behind the galaxy, let's call it a star or another galaxy, doesn't matter which. And again, here you see kind of the same shape as you saw in the previous diagram. The light rays from this background source are being deflected around the sort of intermediate source and coming at the guy's face from two different directions. So he thinks he sees two galaxies, here and here. So one of the tricky things about the lens equation is it does not have a single solution. It has multiple solutions. That's actually incredibly important and a very fundamental property of it. So what's sort of being shown here with the two equations is that there are, in principle, two solutions to this equation. One solution describes each image position that the guy actually sees. And they both originate from the same source and the same foreground lens, or intermediate ground lens. So understanding the lens equation is critical for what I do. The real nastiness is really all in alpha here, which is why I've only shown it as alpha as opposed to what it can actually look like if you write it out. And alpha describes the way in which this thing causes light to curve. The other term here is just DLS over DS, and this is just the distance from the observer to the source and the lens to the source. So that's a simple geometric thing that we're not really going to talk about anymore today. So how does gravity go about bending light? This is kind of a slide stolen from the internet, except it's exactly a slide stolen from the internet because you can see Wikipedia here. If you have seen specials, you see this a lot on things like the Science Channel or the History Channel. Gravity is called a force, but it can actually be conceptualized as the curvature of space and time, which sounds maybe like sort of high-minded and hokey, but it's true. And it's very easily visualized, actually. If you think of the space and time as just a grid, which is represented both here and here, and gravity is just what happens when you introduce mass into space and time. So here we've introduced something like the sun and some other sort of star here, and each one bends the grid and causes it to curve. And that curvature is exactly the way that gravity curves space-time. This is relevant to lensing because the curvature is what causes the light to actually curve its path. So what's shown here is actually kind of a schematic representation of the first gravitational lensing experiment that was ever conducted. If you've read the history of this, it's actually kind of interesting. It was the first prediction of Einstein's general theory of relativity that was tested. And it was done via an expedition to the South Pole in like 1909 or something crazy like that. And it was basically using an eclipse of the sun to actually look near the sun and watch the sun gravitationally lens a background star. So from Earth, they looked, they thought they saw a star located here, but in fact they knew because they could look at times when the sun wasn't there doing this. The star was normally located here, so you can measure the displacement from the apparent location of the star to the real location of the star. And you can just know, or you can infer then that light, the travel path of that light has been deflected. And so this is exactly how gravitational lensing works. In this case, it's the sun. What we actually deal with, going to have to pause this at a few points because I am long-winded, are not, or what I actually study, stop it, well, whatever, I can talk fast, are not stars, or we can just watch it several times. Not stars, gravitational lensing other stars, but galaxies, or more in the case of what I do, clusters of galaxies, which is what this is. Each little yellow splotch here is an entire galaxy. Clusters of galaxies lensing background galaxies. So we'll go through this again. What happens here is they're setting up a simple schematic. We have an Earth, an observer like me is looking at a background galaxy, and they're introducing a more and more massive object in between the two. And so light rays from the background galaxy are being bent more and more. And when this thing is massive enough, the rays kind of both meet back at Earth, and we see multiple images of the background galaxy. And the really cool thing here they do is superimpose an actual image from the Hubble Space Telescope of an actual well-known gravitational lens, where this is actually happening. So I think that's a pretty great video to steal from the internet for the purposes of this talk. And we can go back to the still schematic if we want to explain what's going on here. So again, you see this sort of representation of space as a grid, this really, really incredibly massive collection of galaxies. You know, think our Milky Way, which if you've seen it in the dark sky is pretty huge, right? Except this collection here has typically thousands of galaxies, at least as massive as the Milky Way. And so that's what causes this. This causes the lensing effect and the bending of the lights. Alrighty. So we're going to go back and go over once more a little bit about how this actually happens, just to get one more point across. I mentioned there are multiple solutions to the lens equation, and multiple doesn't just mean there are two. There can actually be quite a bit more than two. And actually, when I say that there's two, that I'm lying. There's actually always an odd number, but one of them is always, like one of the images is always really hard to see. So we usually speak in terms of the even number of images you can actually see. So hopefully that will not get too confusing if I start correcting myself. But what's shown here is just two possible scenarios where you have, you know, a two-solution, two-image gravitational lens situation, foreground lens galaxy. There's some background source, and you see two images of it here and here. And this is just a situation where you have the foreground lens in the middle, and then four images, A, B, C, and D, of some background source. So hopefully we all have a good picture in our heads now of how gravitational lensing works. So we're going to get into some real data. These, if you came to the website to actually that promoted the talk, they had an image very much like this next to my name and my face. And I wasn't actually able to find the actual image that was put on the website, which is kind of embarrassing. But it was one out of an entire sample that was created in the, I guess, early to mid-2000s by a guy, Adam Bolton, who was here at Harvard, who is a very nice guy. I know him. And these are lenses that they found in the Sloan Digital Sky Survey, which is just a large survey of the entire northern sky. These lenses are relatively simple. They are not clusters of galaxies. They are just a single galaxy. In each case, the big orange thing in the middle is just one really, really massive galaxy. And then the blue stuff that's all around it are actually multiple images of some background source. Now, in this previous slide, I showed images as kind of points, right? So in these situations, you're actually, the background thing that's being imaged here is, well, here, here, and here is actually what we call a point source, an incredibly small object. And what's being seen here are larger objects that instead of like showing 4 points, when you see 4 images, you actually see 4 smeared, distorted images that can actually smear into one another. And in the case of the picture that was on the website, produce an actual full ring. And in some of these cases actually produce kind of the full ring a little bit. But these galaxy scale lenses are identifiable by the fact that they produce full rings or approximately full rings. That is, you get a nice, neat, circular kind of lensing shape is the word I should be using. So that's kind of a galaxy scale lens. That's something closer to the lens you might have in your eyeglasses. It's a fairly smooth lens. It's well behaved. It's somewhat easy to understand how this lens works if we want to use it to do science. But that is not the kind of lens that I use. Why make life easy when you can make it difficult? I'm going to show you what the distortion of a cluster of galaxies, a gravitational lens of a cluster of galaxies looks like. So here you have a lens, you know, one giant galaxy sort of lenses a ring around it. What we're going to talk about is this galaxy with, you know, thousands of others around it, where the lensing features, the blue stuff, are on much larger scales. And the mass distribution, or sorry, the lensing, I keep slipping into math terms here. The lensing distribution, which is just the thing that does the lensing, is not so smooth at all. It's actually really, really clumpy. This is what happens if you grid a perfect, or lens this perfectly even grid with one of these really, really massive gravitational lenses. This is why I used the funhouse mirror analogy earlier. It's really quite insane what happens. So yeah, that's always kind of fun to look at. But So it's really actually, so this is why I showed you the lens equation earlier, because we're going to be using the lens equation to solve for the shape of the thing that's actually doing the lensing. If we want to use this thing as a natural telescope, we need to know how it's shaped, and we need to understand what it's doing to things behind it. And that's kind of a hard problem, but it's something that a lot of people have been working on for a number of decades, and it's pretty well figured out. So moving on, I can't go on here without talking about my thesis work. So this is part of the sample that we actually discovered as part of my thesis. These are galaxy cluster scale lenses. So in each case, you see a lot of orange stuff, right? So all the orange things are basically the foreground galaxies, the lenses. And typically you see one dominant one in the middle, or sometimes two dominant ones in the middle in this case. But you always see quite a few of them in the field. And similar to the other images, sort of the bluish or purplish things that you see stretched and distorted, those are the background galaxies that have been lensed. And note, really only in one case here, possibly two if you're going to talk about this one, do you really see this full ring structure. For the most part, instead of seeing this nice ring, you see things that are arcs, or in this case, it's an arc plus some other image that's kind of pulled out over here, or arcs kind of broken up like that, or just one single continuous arc. So when you see this kind of structure, this is a clue that you're not getting the nice, smooth, circular lens that you get from a galaxy scale lens. You're getting a much nastier mass distribution. Nasty just means difficult to solve. So the question is, how do we actually solve these mass distributions? And the answer is with the lens equation. You measure positions of galaxies that have been distorted. And in fact, you measure positions of individual pieces of galaxies that have been distorted. And those just serve as constraints on the lens equation. So you just solve it iteratively, and I'm not going to go through that process here. That would probably be super boring. But you ultimately end up with a constraint of alpha. And once you've actually solved the lens equation, you can go on and do your science. Right. So we're going to step through that process of finding images to solve the lens equation, because this is what a lot of people spend a lot of time doing. What's shown here is one of the most famous lenses known. It's Abell 1689. It was one of the first lenses discovered, and it's also one of the best. If you look at this image closely and for a while, you'll see dozens upon dozens of features that are kind of obviously gravitational lensed. All these long, streaky things all around. Those are all different background sources that are basically being distorted through this sort of crazy optical system. And in total, there are over 100 background sources that have been distorted and lensed in this way in this cluster. So that sounds like a lot, and it is. And the good thing about having a lot of galaxies distorted that way is that it gives us a lot of constraints on the lens equation, so we can solve the shape of the lens extremely well. And the way we do that is by iteratively finding more and more pairs. You have to do a lot of stuff like identify things by color. So those of you with really good eyesight might see a small red blip zoomed in each of these squares. That is an incredibly distant galaxy that has the same color in all different positions on the sky. And so you can basically measure the color of these things, say, oh, these have exactly the same colors. They might be the same galaxy. Feed it into the lens equation with all the other stuff you already have, all the other lens sources you already know about, and confirm that it does seem to be one source imaged 4 times, and it provides another constraint in the lens equation. We can also find things that have been lensed by shape. So in this case, this is actually pretty cool. You see one galaxy that's got kind of a bright knot, a fuzzy tail, and then some tiny little faint knot over here. You see another galaxy that's exactly the same basic morphology over here. A bright knot, kind of a fuzzy tail, and another bright knot over here. And up in the corner, you can see 2 more images of basically a more distorted version of this galaxy, right? It's a bright knot, a fuzzy tail, and a faint knot over to the side. And so just using the shapes of these things that appear all around the center of the lens, you can once again deduce that these are probably the same galaxy that's been imaged 4 different times in this case. And there are ways we can confirm that they are the same galaxy using follow-up data, which we do. There are also some really crazy morphologies. You get actual resolved, these are big old resolved galaxies where you've got kind of a red core and some blue stuff kind of floating around, and it's one big giant galaxy. And you see basically the same thing, excuse me, in other locations. This is kind of washed out by the nearby light. But so what a lot of us spend way too much of our time doing sometimes is finding these image systems, providing constraints to solve the lens equation, and understand how exactly, there's one more to go, there we go. How exactly, in this case, Abell 1689 distorts light behind it. Whew. So a lot of the next few slides are going to focus on this system, which I've been showing you already is the background for a number of slides. It's one of my favorites, possibly my favorite, not only because it's my sort of collaborators that discovered it, it's also the most, I would say, spectacularly bright lensed source known about yet today. if you guys know about the history of astronomy, there were sky surveys conducted in kind of the 40s and 50s using the Palomar and smaller telescopes out in California. And these were done using photographic plates. So not like a nice digital camera like we have now, but some old photographic plate. And in the photographic plate surveys, which exist just in stacks and shelves at the old library, at the old Palomar Mount Wilson Observatory, you can actually see this giant arc in photographic plates taken in like the 40s. It's just that no one knew to look for it there. So unfortunately, it remained undiscovered until we found it. What I showed you here was an image from the ground. This was actually taken, doesn't matter where this is taken. It's taken from the ground, obviously taken from the ground because it's so fuzzy. This doesn't look anything like the images I was just showing you of Abell 1689, all of which was Hubble data. This is what happens when astronomers use telescopes that have to look through the atmosphere. The atmosphere is a real pain in the butt, and it smears things around, and that's no fun. Which is why Hubble is such an important tool for astronomers. It gets past that whole atmospheric business. It allows you to really zoom in and get the details. And you can imagine that if I'm going through the exercise I just showed you of matching up different images of the same galaxy using shape or using color or using sort of how it's configured, having this kind of sharp imaging is essential. You cannot do that stuff from the ground. So we always have to go to Hubble to get that kind of information. Oh, yeah, interesting factoid. I had actually, well, we'll go back to that. Yeah, statistics of this system if you're curious. The lens itself is quite far away, all the orange stuff. I think I gave the number somewhere up there. Yep, 6.8 billion light years away. And the background source, the blue thing, the arc over here with a counter image here, so there are 4 images there, is even farther away. It's when the universe was kind of 35% of its current age. So kind of a nice system. I'm going to focus in here because we got to look at pictures of the night sky from various dark sites and or fake dark sites that were called cities. You saw the Milky Way sort of imaged or showing up on this projector, right? And if you've seen the Milky Way in the night sky, you know it's not only just a band of light. You can actually see structure. You can see like dark regions, right? You see dust lanes is what these are. These are clouds of dust in space that actually obscure light behind them. So you just see them as dark shadows. That's the Milky Way, which is kind of surrounding us. This galaxy, which is 9.7 billion light years away, is so highly magnified by the lens that nature has provided this that you can actually see dust lanes in this galaxy, which is frankly insane and blows the mind of most astronomers who see it for the first time. So that was just worth showing off. And once again emphasizes what Hubble provides us that is just simply not available from the ground. So we went through that exercise of reconstructing the lensing potential, understanding how the background source is gravitationally lensed. One of the reasons that we do that is to understand better the source that is being lensed. So I mentioned we have to solve the lens equation, understand how the lens works. Once we do that, we can actually take the images that we have of the lens galaxy. So I mentioned one here, there's one here, all of this is another one, and then this one over here is the third, or the fourth. And we can actually reconstruct what this galaxy would look like if the lens were not in the way. And so this is what you actually get from what's called a source reconstruction, just a reconstruction of that background source. And once again, just to emphasize the spatial stuff, this is a galaxy that's in some ways maybe not entirely unlike our Milky Way. It's probably going through a very sort of active phase in its life where it's running into other galaxies and merging a lot, but you can actually kind of see what looks like a spiral arm, which is kind of nuts. But we're zooming in here in the source reconstruction onto physical scales, really, really tiny scales that you simply, are simply impossible without gravitational lensing. If this galaxy were just sitting here without the foreground, the orange, the lens stuff in front of it, it would be located here in the sky. You would see only one of it, and it would be about this big. And so we would never be resolving all this internal structure. So this is one of these places where we use the gravitational lensing as a tool to get information that's simply not available using resources we have on the ground and the stuff that we see in the sky. So this is one of my favorite slides of all time. We're kind of building up to this one. So there's a lot going on here. But again, it's just the same system we've been looking at, right? Everybody recognizes this stuff. I've got the giant arc, is what we call this thing, the 3 distorted images, 1, 2, and then 3 of this background source. And I've got the reconstructed source of what it looks like intrinsically if it were not being distorted by the lens. So it's going to get kind of personal, but the science or the sort of the observing that I spend a lot of time doing is spectroscopy. I mean, I don't know why it's personal, but anyway, it's personal to me. It takes up a disorder or a ridiculous fraction of my time at least, so it feels personal. I'm a little uncomfortable you said that, so thanks. So spectroscopy is the observational technique that I am, I guess, most familiar with. Well, that's not really true, but it's what I use, but what I spend most of my time doing. So everything I've shown you so far is imaging. So we take images in astronomy. That's important. We have to know what things look like. But imaging is very limited in terms of actually sort of digging into the details and understanding what a galaxy is made of, what exists in space, like what's out there. You can't really get that very well from imaging. What you have to do is, study the spectrum of objects in order to actually understand what's there. And so I've drawn just a very simple schematic. This is how we do spectroscopy. We put what's called a slit on the sky. So the white region here is just the slit. What it actually is a thing in front of an instrument, and it blacks out the whole sky except for what's in the slit. So in this case, the only thing that gets through the telescope to the instrument is the light that's coming through this white region. And then we disperse. Ooh, that's the wrong direction. Disperse that light in sort of the classic prism effect, rainbow, same kind of thing. And we see its constituent colors, and we can actually look for detailed features in the spectrum that tell us about what's going on inside this galaxy. And the things you see basically are signatures of various elements, and from the ratios of those signatures, you can actually measure things like how hot stars in the galaxy are, how old the stars are, how much of different elements there are. There's actually kind of a laundry list I could really go off on there, but I'm going to restrain myself. And this is really where the bulk of the information comes from when you're studying objects out in space. So the really cool thing here is that we put this slit along this arc several years ago, before we actually had the source reconstruction. And so you get all this light coming through the slit, and you get this spectrum, and you measure stuff, and you're like, wow, there's, okay, if we look at the spectrum that comes from sort of this region on the slit, it's different from the stuff coming from over here. That's kind of strange. It's kind of strange looking at one galaxy, but what we're actually seeing there are spectra from two different regions within the same galaxy. And later, once we had the data and had gone through the process of actually solving the lens, making the source reconstruction, we're actually able to recreate what the source looks like if the lens were not there, and then also recreate where the data that we gathered, what the slit was effectively doing in this plane of the galaxy, if that makes sense. So assume putting the slit here on the sky, on this distorted image, was effectively, assuming the lens had not been there, like the same thing as putting the slit folded in this crazy way on the galaxy, sitting back in its sort of distant location where it actually resides. So that's kind of nuts. And what's actually happening here is that the slit literally is folding over and wrapping around itself and then coming up this direction. And hopefully this helps to visualize it. But the reason it's cool is that we can actually then take points here and map them back to the spectrum and say, wow, okay, now we know that this whole part of the spectrum here, all this light that gets dispersed, it turns out is only coming from this tiny region right here, because that's where the slit is really getting folded a lot in on itself. That's where things are getting really highly magnified. And then the stuff that I've actually covered up with the example spectrum, these knots up here, see a blue thing, kind of a red thing, and a blue thing, are actually these blue, red, and blue knots over here. So now we can actually not only reconstruct what the galaxy looks like with incredibly fine detail and incredibly high definition, we can actually go back to our spectrum and say, oh, now I actually know what physically is going on there. I know what kind of stars live here, what kind of stars live here, what kind of stars live here. You also get structural information from the spectrum. I know how these things are moving with respect to one another. And you can really build a picture of what's going on in this galaxy that is, once again, 9.7 billion light years away, to a degree that is normally only available for galaxies that are much, much closer to us. This is an exploration of the high redshift universe that is impossible without gravitational lensing. Whew. I'm zooming through these. So that's one great science result that I was personally involved in, so I kind of showed it off, and I'm obviously very excited about it. This is another one that I was not directly involved in, but is also just super exciting. This is just a few months old. This is a different lens. Hopefully you're becoming a little familiar with this by now, because I'm not going to spend too much time on it. But again, all the orange things are the galaxies sitting kind of in the foreground. They're acting as the lens. And in the background, you have things that are being lensed. I'm trying to think, there aren't as many obvious ones in this field. This thing and this, I think these are all images of the same background source. And there are a number of other image pairs that are just less dramatic than the other stuff I've shown you. Excuse me. But the exciting result was once they actually observed a number of these background image pairs and solved the lens, they could start looking for things that were farther away than anything we've ever observed. And this is quite a lot of Hubble data went into this image. This is part of a large program that's taking just a few of these lenses and looking at them over and over and over again. And so you're getting really, really deep images sort of around the lens, and that's using it as a natural telescope in a very effective way. And what they found were 3 images. You could never see them unless you actually got, like I can kind of see them now, but if you're never going to see them sitting down, but there are 3 images that I've zoomed out here of the same source, which is a single galaxy at redshift 11, which means 13.2 billion years back in time. We're looking at light that is 13.2 billion years old. If actually haven't computed this number for the new Planck satellite results, but the universe is approximately 13.7 billion years old. So that's when the universe was 500 million years old, or approximately 4% of its current age, which is really just kind of mind-blowing. This is the first discovery and what is hopefully a new string of sort of sensor probes of the very distant universe. That sounded very wordy. So I'm going to kind of recap what I've gone over here. Lensing. We use multiple images to reconstruct how lenses work. I didn't actually show this, but when you make a lens mount and you solve the lens equation, these curves are kind of what you get out of it. It just looks very fancy, so I had to kind of show it off. You get a source reconstruction. That enables you to do things with an incredibly high precision. You can study things in detail that simply is not possible without all this having gone through this procedure, without having the natural telescope there to help you. And once you understand natural telescopes, you can use them in ways that let you discover things that are farther away than anything you've ever seen before. That's pretty cool. So I mentioned at the start of this talk that this event is pretty well timed. And the reason is, I think Christine mentioned I've been traveling a lot. This first half of this week, I was in Baltimore, which is where the Space Telescope Science Institute is, which is the contractual agency that runs the Hubble Space Telescope. Because Hubble cannot be run by government employees. It has to be run by independent contractors. There are a lot of weird rules there. But that's where I was. And it was for a symposium, well, they called it a workshop, on what's called frontier fields. And this is a new initiative that basically went from, it's emerged from nowhere basically in the past year, where the director of the Hubble Space Telescope has decided to spend a lot of the time that is at his own discretion in terms of how to use, and he gets a lot of that, doing nothing but pointing at 6 of the most powerful gravitational telescopes we know. What's shown here is a plot of the sky. RA, hours, is just kind of like longitude, and declination is basically latitude, and it's projected out in the sky. Or this is a projection of the sky that you would see sort of from various longitudes and latitudes. What you see as the curved region is the Milky Way. That's how the Milky Way looks when you do this. And what you see is sort of dark blue-purple regions are regions where the Milky Way is not in front of us, or not in the way. So these are the sort of places in the sky where we can look out and not have to look through our own galaxy. We have the clearest view of the distant universe. And what's plotted as black points are the locations of the 6 clusters that are going to be used as giant cosmic telescopes. So these 6 clusters are called the frontier fields. They're incredibly powerful natural telescopes, and Hubble's going to look at them for about 1,000 hours, which is a lot of hours. And the data set this will produce is the deepest survey of the universe that we have conducted to date. And the meeting was all about those of us who actually are sort of familiar with lensing and deal with it every day, discussing about the best way to go about this and how best to use the data. So it was a pretty exciting meeting, and certainly a lot of work. But this result actually kind of came out just in time for that meeting, which is why I was able, this result, to show it to you. So that's what I meant by well-timed. Well, I think that's all I had, so hopefully you enjoyed it, and I can answer a lot of questions, which hopefully there are. Thanks.